Good morning, everybody. My name's Sheila. I work for the Royal Astronomical Society. I'm the Education, Outreach and Diversity Officer. And it's absolutely fantastic that we can welcome you here today for an audience with the last man on the moon, the astronaut Gene Cernan. Just a little bit of housekeeping before we start. So I've muted you all so it's not too noisy, but if you want to ask any questions to Gene or if you want to say anything to our astronaut, then please type your questions in the chat function. I'll make a note of them and we will get those questions to Gene. And we are recording today, so if you don't want your faces to be recorded, please switch your cameras off and enjoy the show. So I would like very much to introduce our very, very special guest for us today, and that is astronaut Gene Cernan. Oh, we can't hear you, Gene. Let's see. There we go.
Is that good?
Oh, there we go. Fantastic.
Fantastic. That's good. I was worried about that because I was trying to press buttons and nothing was happening. Morning, everybody, or afternoon, evening, wherever you are. And I've been hearing down the line a few people who've got birthdays today. A very happy birthday to anybody whose birthday it is today. And lovely to see you all. Lovely to see you all. So, Dr. Kanani, how do we start?
We can start with you. It's completely up to you. What do you want to start with?
Well, I guess the first thing people ask me about is actually taking off from in a rocket from Cape Canaveral, and I've been in space 3 times. So I was on a flight called Gemini 9, where there were just 2 of us in the capsule, and then Apollo 10 and later Apollo 17, where there were 3 of us in the capsule. So this was a much bigger rocket, the Apollo Saturn V rocket. And we've got to go phenomenally fast in order to get out into space. So if you can remember, or you can visualize, or we have a picture of the actual rocket itself, the Saturn V rocket. I've been doing a little research about London, and I understand I've got this right. There's a place, St. Paul's Cathedral there. And apparently it was built by a man called Sir Christopher Wren, 365 feet tall. 300, because he reckoned we'd have a foot for every single day of the year. Our rocket was 363 feet tall. So if you can imagine a rocket that's just a little bit shorter than St. Paul's Cathedral, that's how big our rocket was. It had 3 stages to get us up into space. And everybody knows that we go 10, 9, 8, the countdown. At 8 seconds, the rocket at the bottom starts and the whole thing starts to shake. You've got a huge amount of vibration. You've got a huge noise. And then at 0, the thing is released and we lift off from the launch pad. Very slowly as it happens. You probably get away quicker in an automobile, in a car, than we do initially with a rocket. But it doesn't take long before as we get rid of fuel, we get faster and faster and faster. The first half of the rocket, the first stage of the rocket, takes us up to about, I suppose 40 miles high, out into space already, 40 miles high, and a speed of about 5,000 miles an hour, which sounds very fast, but in fact, if we were to switch everything off, then we just fall back down to the ground. So the second stage then lights up. That takes us up to about 115 miles high, and we're doing about 15,000 miles an hour, still not fast enough. So the third stage takes us up to about 117 miles high, and then we're doing about 17,300 miles per hour. Now, that's a lot of numbers I've given you. 5, 15, 17. You think, whoa, how's all these numbers? Don't worry, I can see 1 or 2 parents there in the background. They've remembered them all. They'll remind you of what they were when I finished. But those speeds are quite crucial because 17,300 miles an hour is a balancing act. This is where, if you imagine that this is the Earth, we're actually going fast enough that we want to go in a straight line. But of course, the Earth has gravity and it wants to pull us down. But we're going just fast enough so that we don't fall down, and not too fast so that we go straight on. In other words, we're going into orbit. 17,300 miles an hour. How fast is that? It's about 5 miles per second. So if you think of a journey that you've done maybe 20 miles away, maybe you go to see grandma, grandpa, or you go to a place, you know, you visit quite a lot, 20 miles away, 5 miles per second. We would get you there. Anybody worked it out? Can anybody put their hands up and see how many seconds that would take? 4 seconds. 4 seconds. That's how long it takes us to do 20 miles. And we're in orbit. We're now in space, and we're ready to get our mission really launched. Another question I've asked, okay, so you've taken off. Why do you float around? What happens? Everything floats around. Here, everything floats around. A lot of people say to me, well, because you float around because there's no gravity in space. There's lots of gravity. Do you remember I said that the Earth here wants to pull us back? That's got gravity. The moon has got gravity. The gravity that makes it go around the Earth. The sun has got gravity. Loads of gravity out there. It's just that while we're out in space, because we're trying to be pulled back by the Earth, we are always falling. We are always falling. So I just got a little object here. It's a glasses case as it happens. You can do this with anything. At the moment, that glasses case weighs something because it's pushing down on me and I can feel the weight of it. And if I let it go, gravity makes it drop. And momentarily, while it is falling, it weighs nothing. Here's a very silly experiment not to do, okay, not to do. So you take Marpar up to a cliff edge and get yourself some weighing scales. Look down on the weighing scales and you'll see how much you weigh. And don't look at mom and dad, they might be a bit embarrassed. And then make sure those are strapped to your feet, because as you jump off the cliff, you'll suddenly find that you don't weigh anything. So in fact, that if you got mom and dad next to you, you could get your little finger and theoretically you could just move them with your finger under their chin like that. And we can do that in space. While you are falling, you won't weigh a thing. You are weightless, weightless. So there's still gravity, but things don't weigh anything out in space. And that's why we float around. It's very easy to get used to, doesn't take long, but it does make one or two things a little bit difficult, as we'll see. Eating, sleeping, and as we'll come to, I'm sure somebody's going to ask the question, how do we do a poo in space? That too becomes a little bit difficult. And also, we're not actually built to go up into space. So the first thing you'll notice is that when you got up this morning, you probably don't realize this, but your head had a little conversation with your heart, and basically the head said, hey, you need to pump some blood up here because, you know, they're getting up. We need to get some blood into our head. So your heart pumps blood up to your head, and you're stood at the moment, and the blood goes down to your feet. That's the way it works. So when you're doing that, we're used to that. Now imagine if you turned yourself upside down. Where would all the blood go to? Would it stay in your feet or go down to your head? All goes down to your head because heart wants to pump blood to your head. So up in space, that's what it does. It pumps blood up to your head, and bit by bit, your face starts to puff out. You get really red and puffy. And people look at you and go, yeah, are you okay? You okay? Well, fine, but you look a bit strange. And our feet are crying out for some blood. We're cold down here. Get my grandmother's bed socks. We're cold down here. So your body has to adjust to getting fluid from your head, from blood from your head down to the rest of your body. One of the ways we have to do that to reduce our fluid in our body is actually we have to pee quite a bit. Because that reduces the fluid and helps us actually get the circulation going. And the other thing is, I wonder if anybody out there, I'm sure there are people out there who get a little bit sick when they go on a plane or a boat. Yeah, anybody do that? And because we're floating around, you'll find actually a lot of astronauts get up into space, and one of the first things they do, they have to get a paper bag and be sick. So first things in flight, we're floating around and we might have a quick pee and be sick. Other than that, it's a wonderful sensation. It really, really is. It takes about 24 hours, maybe a little less to get used to it. Have we got any questions so far, Dr. Kanani? or shall I press on?
Yeah, we have a few. We can do a few now and keep, keep
Sure. Sure.
going. Okay, so one of the first questions, what is the biggest rocket? What is the biggest rocket?
The biggest rocket is the Saturn V to date. That is the biggest one we've ever built to send man into space. So yeah, 363 feet tall, about 320 tons, I think, weight lift, and 7.5 million pounds of thrust. So it is an incredible machine, largely built, it has to be said, on Second World War technology. But it is a phenomenal machine. So that's your answer. That's the biggest rocket to date. No doubt they're going to get bigger and better because we got to get further and further out in the space. We'll need bigger rockets for bigger payloads.
And related to that, why do you have to release bits of the rocket in order to go up?
Well, that's a very good question. There were a number of different concepts for how we were going to get men into space, but also to the moon. And one of the things you could do is have just a huge, ginormous, long rocket. But the problem is the thrust of the rocket, has not only got to get us into space, it's got to get the rest of the rocket into space. And if you have a huge, huge, huge engine, of course, it poses its own problems anyway. But the thing is, if you look at the Saturn V and you jettison the first stage, now that is about half the rocket. Now, if you think about it, if something weighs less, but you push it just as hard, it's going to go faster, isn't it? So let's suppose I've got this ball and I throw it with a certain amount of push. It'll only go so far. If I want to push it a little bit harder, it'll go higher. If I, make things lighter, but still have the same amount of push, they're going to go faster. So by cutting half the rocket off, but still having the same amount of push on the second stage, that means I can go much faster. And when I've got rid of that, I'm up into space. It's much more fuel efficient. It is also technologically easier to build, as I understand. And it makes the technology easier, because every pound of whatever, human being and so on and so on, that we have in the rocket, we need 15 pounds of thrust. So if I can reduce that weight as I go up, I can actually do it with less fuel, smaller rocket, and so on and so forth. Other designs, for example, had us coming up with one rocket that went out into orbit, another rocket that set off to the moon, and then we would link up at the moon. And all of these things were thought about, but sending one rocket up that we could stage turned out to be the most efficient. The designer of the rocket was a man called Wernher von Braun, and he was pretty well a genius. So I think he got it right.
Okay, let's have a look. How heavy was your suit? How heavy was your spacesuit?
The spacesuit that we walked around on the moon is about 90 pounds. Although as we get to the moon, I'll explain, of course, there's less of a gravitational pull on the moon. It's about 1/6. So if you think about a 90-pound suit, it actually weighs about 15 pounds. This is a concept that sometimes people find is a little bit difficult. As a person, I have a certain, what I call, mass. Now, if you're on the Earth has a pull of 1g, and your mass will make you weigh whatever. Let's say 12 stone. Keeps it nice and simple. If I go to the moon is smaller. It has less gravitational pull, about 1/6. So it'll actually pull me down. But if I put some weighing scales there, I would only weigh 2 stone, because I weigh 1/6. So everything that I talk about, the weight of the suit and the backpack and so on and so forth, yeah, it's quite heavy. But because gravitational pull on the moon is a little lighter, a little less rather, I won't weigh so much. I still have the same mass, still got the same me. I don't, the bits of me not falling off or anything like that. I still got the same mass, but because I'm being pulled a little less, it is actually lighter. The problem with the suit, to be perfectly honest, all suits, is, getting it sorted out and making it less cumbersome and tight and so on and so forth. maybe when we get to the moon, I can tell a little bit more about the suit itself.
Okay, we do have some more questions, but we'll let you carry on for a little while and then we'll do some more questions.
Okay, so we're going in orbit, but we don't want to stay in orbit forever. We want to go to the moon. And so I think I told you that we were doing about 17,300 miles an hour, about 5 miles per second, roughly speaking. We're now going to go towards the moon. Now, here's the thing. You look up at the moon at night and you think, yeah, I could fly up to there. It is not a stationary object. We're not going to go from the Earth to the moon. Remember, the moon is actually orbiting the Earth itself. So what we have to do is not go to the moon, but rendezvous with the moon. And that is a bigger thing than it sounds. So we set off from the Earth, and our object is to rendezvous with the moon just at the right time so that we can be captured in its gravitational pull and then go off ready to land on the moon. Now, this is where I mentioned Sir Christopher Wren earlier, another man of that time, Sir Isaac Newton. This is where his mathematics comes into play, because we have to set off just the right time. Too early, and what's going to happen is the moon will be here, and we'll be too far away, and the moon will be saying, hey, come over here, come over here. And we're going to be too far away. It's not going to be able to pull us in. And if we're too early, we'll go straight past, have a vacation on Pluto, which we don't want to do. If we set off too late, then the moon may be literally in our way, and our space rocket will come along and crash into the moon. The distance from the Earth to the moon is 240,000 miles, give or take a bit. 240,000 miles, about 250,000 miles. And in order that we don't arrive too early or too late, we have a little window of opportunity that we have to fly into. And that gap is only 50 miles, 50 miles, 50 miles. So we travel all that distance. We got to make sure that, according to Newton's mathematics, we get in that little gap. And so that's why when we set off, we'll go at a tremendous speed. We want to escape Earth's gravitational pull. We go from 17,300 to 24,500 miles an hour, roughly speaking. That's going from 5 now up to 8 miles per second. So if you remember that little journey we were talking about of 20 miles, it was going to take you 4 seconds. Now we could do that journey in 2.5 seconds. You're there. It's very fast. I wonder if there are some grown-ups in the room. Let's see if they're good at math, shall we? I can see one grown-up going already, but we'll see. I'm going to set you a little sum. Because the moon is 240,000 miles away. It's usually the kids who get this one, by the way, but don't worry, no pressure, grown-ups. The moon is 240,000 miles away. I'm going to say our rocket goes at 24,000 miles an hour. So how long should it take to get from the Earth to the moon? 240,000 miles at 24,000 miles an hour. I'm just going to give you a little second or two to work that out. And folks, if you've said 10 hours, you've done the maths very well, but you haven't done your Newtonian maths very well, because, of course, we've got to remember that the Earth has gravity and the moon has gravity. So as I set off from the Earth, just like when you jump up from your seat, the Earth will be saying, hey, come back here, gravity, hey, what you doing? So as I set off from the Earth, I'm slowing all the way down until I get to about 200,000 miles out into space. And then the moon says, hey, come on down. I got a little bit of gravity. So I slow down and then I speed up again and get into lunar orbit at about 5,000-6,000 miles an hour. So instead of that taking 10 hours, as you correctly worked out, it can take 65 hours, about 3 days really, because we're slowing down and then speeding up. It's the same thing. It's a little experiment you can do if you've got a ball or something like that. You know, when you throw it to somebody, you know how to get it in their hands. You've got to set it off really fast, and as it goes up, it slows down, and then it speeds up again and they get it in their hands. It's the pull of gravity. So we use Newton's maths, his work on the effects of gravity, to get us away from the Earth, and then just free ride little correction here and there maybe until we get to the moon, and then we get into orbit. And then we're ready to land on the moon. We've got to do housekeeping though. And I mentioned earlier that, you know, we have to eat, we have to sleep, and yeah, we got to go to the john. We got to go to the toilet. So I will talk about these now because I guess there's the things that people want to know. Sleeping, first of all, is quite tricky because in that weightless condition, you can strap yourself into a harness, but as you sit there, you obviously be aware that your arms will float around, your hair will float around. It gets quite difficult to actually get decent quality sleep. But nonetheless, as much as you can. Eating. Now, eating food is very tricky because everything we eat has got to be in some sort of solid form. If you think about it, some of the foods that you like to eat are not particularly suitable. For example, if you like peas, terrific, but they've all got to be mushed together because if we had a whole pile of peas, they just float around the spacecraft. So you could have mushed peas, you've got to have sort of gunky things that are held together. So typically, we have a cupboard, and it will have your name on it. It's only for you. The food is only for you. And you will have packs of food given to you in a specific order. Meal 1, day 1, meal 3, day 4, and so on and so forth. And little tip, if you do go out into space, you get a little bit dehydrated. You don't have so much, moisture in your tongue. Your taste buds don't work so well. So if you do go out into space, order things that'll perhaps a little bit more spicy, a little bit more flavorful, because otherwise it can be a bit bland. And you would typically have, for example, something like a yogurt, a set yogurt, obviously, not a runny yogurt, a set yogurt, and you'd peel the thing off. And here's the thing. We haven't got room in our spacecraft for a big table and chairs and that kind of thing. So you got to create your own little atmosphere. So we put a spoon in there, and there's our yogurt. You just leave it floating in front of you. Not going to go anywhere. And then your main course would be maybe a tube of granules of powder. You put some water in there, knead it with your fingers, heat it up, put it in front of you. And then maybe at the end, you'd have a chew or a biscuit. Just pop it there. There you have it, floating in front of your own little table. And you can pretend to sit next to that table. And if you want to have a drink, I've got a glass of water here. Now think about this. If I now turn this upside down, I know what's going to happen. In a spacecraft, if I did that, water just stays in there. So when we want to drink water, we actually have a little gun and we squirt it into our mouth. And that makes it easy to have a drink. So those foods, nice and easy to eat. And they used to have a little joke with us sometimes. You'd order something like, chicken and rice surprise. And then when you got back, they'd say, so how was the food? And I said, well, chicken and rice surprise. Didn't taste anything like chicken and rice. Well, that was a surprise. Ho ho. It was sometimes a bit bland. So as I say, have something a little bit spicy if you ever go to space. Now, here's the thing. Not everything you put into a human being necessarily stays in a human being. And so at some point, we have to go to the john. So going back to Newton, and I know this sounds stupid. We're going to talk about some physics before we're talking about doing a poo, but it's very, very important. On that research I did about London, I discovered you had a big fire in 1666. I think I got that right. Have I, Sheila? Have I got that right? Yeah. The year before that, your man, Sir Isaac Newton, sat down, probably under an apple tree, who knows, I doubt it, but anyway, and wrote a big book of math. And you may think, well, what's he talking about that when I want to know how you do a poo in space? Well, this is very important stuff. He wrote down this big book of math, and he said, well, it may seem some very dumb things, but actually they're very important. He said, look, if somebody wants to move, we got to consider the following. Anything that's just sitting there is going to sit there. It's going to stay there until somebody moves it or it moves itself. So if I just leave that ball there, it's going to stay there unless I throw it or I leave it for gravity to take you down. So if some force acts upon it, me or gravity, it will move. Otherwise, just sits there. Body at rest remains at rest until a force acts upon it. Okay, so that seems a bit dumb. Second one seems a bit dumb too, because if I want this ball to go up in the air, I apply a force to it. If I want to put it further up in the air, I have to apply, whoa, more force to it. Just like the rocket. If I got half a rocket with the same force, it's going to go faster than a big rocket with the same amount of thrust. So that seems a bit dumb. Here's the third one. He said, look, think about everything that moves, everything that moves. If you want to go in this direction, the force that makes it go in this direction goes that way. Think about a wheel. As it turns on the ground, it will push that way. But the car, the train, whatever it is, will go that way. For every action, there is an equal and opposite reaction. So this sounds, a little bit strange. What's this got to do with a poo? Okay. Now remember what you were feeling like and what you did last time you had a poo. I'm glad we're mooted here because we don't actually need to have any case histories. But you know as well as I do that there was a body at rest. I think we know the body that we're talking about, okay? Now, if that body stays there, it's going to get real uncomfortable. So you applied a force to that body, okay? And I assume these are the domestic arrangements you have at home. At some point, it would leave you and gravity, whoo, took over. Okay. Space is a bit different though. You still have the body at rest. You still apply a force to that body. But you remember what we were talking about earlier about being weightless? It gets to the point where normally gravity would take over, but the effect of gravity, because everything, including the poo, is weightless, means it ain't gonna go anywhere. Instead of saying, well, where's gravity? Gravity's supposed to take over at this point. What? So we got a problem. So if you decide you need to go for a poo in space, this was in Apollo, what you had to do was, first of all, tell the other two guys to move as far away as possible. In a spacecraft, that's going to be about maybe a foot, 18 inches. Anyway, they're going to look outside the window really attentively for the next few minutes. And then you would get a plastic bag. On that plastic bag, there'd be two sticky labels. You drop your pants, you get the bag, and you stick it to your butt. And then you apply the force to the body. And then, has anybody ever said to you, when you're feeling a bit Marty or you're feeling a bit, I don't know, lazy, somebody's always said to you, oh, come on, you can work it out for yourself. You know what? That's what we have to do. Because in the plastic bag, there are little finger pouches. That's what you have to do. And then you just hope you've got that bag stuck to your butt, because otherwise, do you remember that third law of motion? For every action is an opposite and equal reaction. If it escapes from the bag, it will float across the spacecraft. And the other two guys will give you a reaction. Not quite the reaction that Newton was talking about. For every action is an opposite equal reaction. Not quite the reaction that Newton was talking about, but you hope to keep it in the bag. Now, here's the interesting thing. And I'm being a little bit naughty here, I know, but let's face it, if we do a little bit of a poo or a, then it's a bit smelly. If you got a dog handy, you can always say, oh, it was the dog, it was the dog. There's no dogs up in space, it's yours, okay? But in fact, we have to own up, because that bag that we've got now, we put it in there, we seal it, becomes what's called a dump bag, and you actually have to write on it your name, when you did the poo, and then that bag is put into a little cupboard and it's stored for later. So that the doctors can then look through all the bags of poo and see what went in and what order it comes out. And that is important, because on a 2-week mission, our bodies don't change that much. But if we're going to go to Mars, we're going to be out in space for months, maybe years. And if we don't have that gravitational pull, think about it. You're sitting there now, and you stand up, you sit down, you move around, your muscles, your skeleton, they all work for you. Now, if you're putting protein into your muscles and you're putting calcium into your skeleton, that's good. But if out in space, your body says, well, wait a minute, we're floating around here. Do we really need this skeleton? Do we need all this calcium? Oh. And if I want to move somewhere, I don't have to push very hard. Do we need all this muscle? No. If we ignore our bodies and we don't make them work with calcium, protein, and all the things that we need, then first person who comes back from Mars may be, you know, terrific. They'll get out of the spacecraft and just go like this because their body will collapse. So we need to learn how to keep our bodies in good trim. So all those bags of poo, now looking through to see, okay, so we gave him that meal that contained the following, how much of it came out? Very clever. And there's one last thing, of course, we drink, we gotta pee too. So if we need to do that, being an all-male crew, we have a tube, you put that part of your anatomy in the tube, and you gently release the urine into the tube. But here's the thing, some of it we will recycle and drink again. Some of it, however, can be evacuated out into space. And there's a common thing that when you see the droplets of urine floating by the spacecraft, it really is so beautiful. And people have nicknamed that the constellation of urinal. It really is beautiful before it vaporizes and disappears. I'm getting real sort of sounds from Dr. Kanani here, so I think I'm going to stop talking about pee and poo. Any more questions, Dr. Kanani?
It's absolutely fascinating. There have been a few questions about being on board on your way to the moon. So what happens if anything goes wrong, or if you get poorly, or you know, that kind of thing? And also, what are spacesuits made from, and do you feel hot in your spacesuit?
Okay, the spacesuits, first of all, there are various layers of everything has an E and E on it, in enes. I'm not absolutely sure about the actual composition of the space suits themselves. But am I hot in it? Actually, we have a sort of built-in cooling heating system. If you have a look at the backpack for someone around the moon, you obviously have oxygen. That goes without saying. You've got to breathe some oxygen. We'll have a little water to, you know, suck to keep ourselves up. And also we'll have radio to communicate. But one of the things also is that within our, basically our jumpsuit, our underwear, there are little tubes, little capillaries. And there's kind of like a fridge system, if I can put it that way. It's on your backpack. And the surface temperature of the moon can rise to about 100 centigrade when we were there. Now 100 centigrade, that is as hot as steam. So it's really, really hot. We would boil, we would frizz. So yeah, we can actually cool ourselves by having this ambient temperature around our spacesuit. One of the times when it got a little bit difficult for me was on Gemini, and I did an extravehicular activity. That means you get out and float around. And the idea was that I was supposed to go out, do various experiments, and then get back in the spacecraft. Back to Newton. For every action, there is an opposite and equal reaction. So if you're on the end of a tether, this thing is making you go further and further like this. And I was fighting to get control of everything. And in that case, I got really hot. I think my heart rate went up to about 160 something or something like that. Pouring sweat, so much so that the inside of my visor actually misted up. And so I got really hot, and that was really quite worrying, because your next question was, what happens if something goes wrong in space? Well, then you got to trust the people you're with, the people on the ground, and your own training. The first thing, of course, you can do in any situation where things are going wrong is go, ah, that's not good. That's not good. You have got to keep yourself attuned to the training. Kick the training in. So with this, a problem we hadn't encountered, a problem we hadn't thought about. And in the end, you know, I was pulled back into the spacecraft. The staff had pulled me back in. And even then, to get the hatch down, he basically had to sort of wrench me in because my spacesuit had expanded and I was hot. But you just have to, because the alternative was for my crewmate simply to say, well, there's nothing I can do. Cut me loose. That would have killed me. But his training, my training, people on the ground, listening carefully and going through the problem. Now, on Apollo 10, we had an issue, for example, with the Lunar Excursion module. As you know, Apollo 11 was the first one to actually land on the moon. But our mission was to take Apollo, the LEM, rather, the Lunar Excursion module, around the moon, separate from the command module and go into orbit. In other words, the dress rehearsal, just almost like, you know, you're going to go and do that speech on a stage, but you just get to the wings. The next person's actually going to go on and make the speech. And we got down and things were going fine. But for some reason, both our guidance systems switched off. We've got two. They coordinate, they'd be absolutely fine. But in the situation that we found ourselves in, somebody cuffed a switch or something like that, both of those systems switched off. So suddenly the LEM was going, I don't know where I am, and started tumbling out of control. That was frightening. For, you know, a good few seconds, we were tumbling out of control, falling towards the moon. But people were saying, right, this isn't happening, this isn't happening, this isn't it. Try this, try this, try this. Switches went back on, everything is fine. And because the engineering was so good, you know, that problem was solved. The big one, to answer all your other questions, of course, was Apollo 13. And there we had a major catastrophe. A tiny, and I mean a tiny little bit of wire, probably about no bigger than yay big there, was exposed. And when somebody flicked a switch, it sparked. That got in contact with liquid oxygen, bang, huge explosion. So this knocks out the command module. That's the bit at the back. Sorry, the service module, I do beg your pardon, with the rocket on it. This is the bit that's supposed to be flying the mission. Fortunately, very fortunately, they had the LEM on there. So you've got the brightest minds really on the planet, and they got to say to themselves, okay, we have a major systems failure. What have we got that works? And what we had got that worked was a command module, that's the capsule, and we got the LEM with rockets that can to help, and a certain amount of oxygen. Unfortunately, the LEM, of course, was built for 2 men to live in for a couple of days, not 3 men to live in for, say, 3 or 4 days. So people had to get the equipment they could and change the air filters and all these kind of things. During this, the temperature of the space capsule plummeted. And one of the astronauts got very ill. He got a sort of infection and couldn't get warm. What you've got to do is just, you know, work through it. Now, had he died or something like that, it would have been, you know, a tragedy. But the other guys were working around him, helping him, and so on and so forth. That just has to be looked through. You don't have drugs up there. You don't have a surgeon up there. All you've got is communications with the Earth, again, with your training and with the bright minds down in NASA who will say, try this, whatever. Certainly, however, you do not fly. You will never be allowed to fly if you are ill or there is any thought that you might be ill. Because if you got something that's going to interrupt your or you're going to impede your efficiency, or of course something that you can pass on to someone, you know, don't sneeze. Don't sneeze near Deke Slayton. You know, right? That's it. You're off. And so it's well to keep healthy. We are isolated from people, isolated from our families prior to launch to make sure that we're healthy and fit. But it's a really good question. Sometimes, you know, you can plan for everything. It's like going on vacation. You can plan for everything. And then when you get there, first day, you eat something that you don't agree with, or, you know, something happens, and you've got to just say, well, I've got the drugs at home, and I've got a doctor at home. You got to sort the issue. When you're out in space, you really are on your own. It's training, it's equipment, and the guys with you and on the ground that you trust. That was a long answer.
We do have a lot more questions, but I think we'll let you tell us about what it was like on the moon and then do a few more questions.
Okay, I mean, what can you say about being on the moon? That is the greatest moment of my life. To be privileged to have not only been on the moon, and I know I was to date the last individual to set foot on the moon, but I was also the person that spent the longest on the moon. You know, we were in there for 3 days, and we also had a lunar rover. So we were able to go further. We were able to explore further. And because we took up Jack Schmidt, who'd been a huge ambassador for Apollo. And, you know, he was hoping to get on a flight, but because of costs, several of the Apollo flights are actually canceled. And he actually got booted onto Apollo 17 because they wanted to get a scientist up there, a geologist. Boy, were we lucky, because while you're on the moon, you don't walk on the moon, you bunny hop on the moon, really. While you're on the moon, you know, you've got so many experiments you want to do and this kind of thing. And I had a bit of luck. We took the Lunar rover across the surface, and then I just kicked some dust with my foot, and it's orange under the surface. And I remember saying to him, I found orange. I found it. Don't move it, he said, until I get there. And we looked at this stuff. We took it back. Some sort of, I'm not a geologist, of course, but he is. Some sort of maybe volcanic activity has been on the moon. Turns out these are tiny, tiny little crystals of glass, orange glass. And it was quite a find. The Lunar rover, okay, I got to hold my hand up here. I made a bit of a mistake. I got out and I kicked the rear fender and broke it. And it showered us with moon dust. We had to fix it with duct tape, but it was still very useful. It got us across the surface of the moon to get away from the lamb. And really, Taurus Littrow is a beautiful mountainous area. One of the most difficult places to land in, as it happens on the Apollo missions, but so beautiful. You can't describe it. And most interestingly, really, one of the photographs that we took was not of the moon, but of the Earth. And we went to explore the moon. And if anything, I think we learned a great deal more about the Earth in some ways, or at least about our attitude to the Earth. We took a picture of the Earth, and it's called the Blue Marble Picture. Again, I don't know if we have that, but the Blue Marble Picture. And when you look back at the Earth, you see this lovely splodge of white and brown and green and blue, of course. There it is on your screen right now. This was known as the Blue Marble. What a beautiful, beautiful picture. And this is the first time you kids, you're used to seeing a picture of the Earth. Our generation had never seen that. And when we look back, well, you have a look at it. How far did you go left, right, north, south before somebody else is there to help us out? And when you're on the moon, especially with your gloved hand, you can put your hand up and actually cover the Earth with your thumb. And it makes you realize just how small, how fragile, how, in a sense, unimportant we are compared to the cosmos. So being on the moon, yeah, I mean, it's got to be obviously the greatest moment in my life, my greatest achievement, and so on and so forth. But in a sense, it taught me about myself, but also about this beautiful, beautiful Earth that we live on, and how we must treasure it. And a lot of the thought and the measures that came out of trying to protect the planet, funnily enough, came about because we went to the moon. Weird though that may sound. One of the things that, of course, you have to realize is Buzz Aldrin described it as magnificent desolation. Nothing has moved it. Your footprint is the first time anything has moved that does. You put your footprint back, you've got a perfect footprint. It's going to be there for billions of years, because unless a meteorite hits it, there's going to be no wind, no rain. The sun will come and heat it, and then it'll go down to the sun will set and it'll go cool again. But that is going to be there. Whatever you've moved, your footprint or whatever, is going to be there for billions of years, just like that. And one of the things I'd actually did before I left was to write my daughter's initials in it, Teresa Dawn Cernan, or Tracy as we call it, TDC. And I always like to think that, going back here, her initials are up there, and they will be up there forever until the moon ends. Who knows, maybe one day they'll have a Taurus Littrow Apollo 17 museum, which you kids will go up to with your children, and you'll be able to look at that spot. So yeah, being on the moon, you just wish you could stay. But of course, it was a very short vacation, unfortunately.
How long were you actually on the moon for?
About 3.5 days. And that meant that we were the longest mission there. And I forget, essentially, I think we did about 15 hours, something like that. And so we're the last, but the longest. And of course, the furthest with the lunar rover, albeit that it was showering us with moon dust. You look at everybody else's pictures. They come down, nice white suit. And by the time they get back, yeah, the boots and they're up to their shins, a little bit dusty. You look at us, myself and Jack Schmidt, when we get back, we look like a couple of chimney sweeps because we've been showered with moon dust. So you can always tell Apollo 17. If they say, is that Apollo 14 or Apollo what? That's Apollo 17. They're the grubby ones. Yeah, last but longest so far.
We have lots and lots more questions, so I'll sort of go through them a little bit. When you going back to launch, what was the G-force on your way up into space? How strong was that?
Actually, the first part, as I say, is quite gentle. You've got this vibration and so on and so forth. It builds up gently. But you remember with the first stage separating, the same amount of thrust in the second stage, you were probably hitting about 4.5, 5G. And that's a problem because you've still got the vibration. And if somebody says, press a button, okay, you can do this yourself. Lie back, shake, and now try and find the button as you're going, and also being pressed back into your seat. So actually lifting your arm to get the right button. It's quite a feat. So that's and we have that thing is the Gforce trainer. That's a horrible thing. You can always black out in it, but that would take you up beyond that. Momentarily hitting a Gforce is bad enough, but it's a sustained one. It doesn't last too long in launch, but it's you do notice it. Obviously, you do notice it despite training.
Thank you. Let's have a look at the other questions. When you get back to Earth, what's it like? Do you have to sort of teach yourself how to walk again? How did that feel?
Yeah, actually, it's a little bit getting off a bike, really. I suppose you've used to being balancing and you've been pedaling, and you just get off, and then you think, oh, that's a bit, but it's soon very, very easy. To be perfectly honest, this is what we're built for. So Earth is very good. It's not so much the physical as I would say, I've been out in space. I've walked on the moon. You need someone like your daughter to say, hey, Pa, the dishes need doing. That's the thing. When you are brought back to Earth, literally.
And did she follow in your footsteps?
Tracy's done, other things, but no, I don't think she's ever going to be an astronaut. But though, I'm looking at some girls here, and it's nice to see some girls that are working because, we've now got more people getting out. One of the reasons, for example, we took men to the moon was that in those days, girls didn't do maths and sums at school. No. I can remember at school, we'd say, right now we're going to separate. The boys are going to go off and do some math and physics and science. And you girls, you're going to do domestic science. You're going to learn how to bake a nice cake for your husband when he comes home. So the chances of a girl ever learning to fly in the Navy or Army or whatever, the Air Force, or let alone become a test pilot, forget it. So we didn't have a pool of women to draw from there, for one thing. Secondly, just in terms of the fact that in a tiny spacecraft, the privacy issue, the equipment issue would be a problem. That's changed. And now, if I suppose I was working now and my daughter said to me, I want to be an astronaut, I would say, go for it. Do it. Why not? Mm-hmm. I can't stop you. And I always have this, I'm the last man on the moon. But maybe out there's the first woman on Mars.
And talking of Mars, when do you think humans will get to Mars?
When we can afford it. Because, every time we think, right, we're going to set a date, 2030, we're going to go to Mars. We will go to Mars. Humanity will go to Mars. There's no two ways about it. But every time we set a date, Suddenly, something happens, and people say, well, we can't afford that now. So we have to, and also there is a kind of technological kangarooing here. Sometimes, you know, with Apollo, we were set a really an impossible goal. You know, I think it was 62. We just, you know, done I think Khrushchev had called it a bunny hop. We hadn't even gone to orbit. Then our president gets up and says, before this decade is out, we're going to get a man to the moon and back safely. We've got rockets that were built really primarily, in the Second World War. We've not got computers that have got any more than 30,000 bits of information. What is he talking about? How are we going to do it? And you know, in a strange way, if the times have been different and we built a rocket, say in the next generation, it would have been easier, it would have been simpler, it would have been, I don't know. So every time we say we're going to go to Mars, somebody says, yeah, okay, but there may be a better technology. Let's wait for that, which becomes more expensive and the thing is stretched out a little bit longer. We'll get there, but it ain't going to be me, that's for sure. It's going to say it's one of you guys are going to go there.
And then when you were on the moon, how far did you travel from the lunar lander? And could you see any other planets from the moon?
You can see, you can see, if the sun doesn't bleach them out, you can see Venus very easily because it's a very bright star. In fact, if you go out in the evening and it's a clear evening, you can see the moon, pole star, and Venus quite easily usually. But it's very, very bright. But in fact, most of the stars are actually bleached out, so you don't see that particularly. We must have got it. I don't know offhand, but I think maybe, half kilometer away from the spacecraft, something like that. We certainly lost sight of it over the horizon. Not too far, so we couldn't walk back, of course, in case the rover broke down. But that's a good question. I can't remember that, but it was so that we lost sight of the LEM for a little while.
And can you cry in space? Did you feel emotional when you were up there?
I felt emotional. I don't remember ever crying. I just felt proud, immensely proud. But if you can do most things that human beings can do, but crying, sneezing, doing anything like that in a space helmet, not really a good idea, because put it this way, if you cry or something like that, it's going to come down and you know your instinctive reaction when you cry? Just wipe it away. Can't do that. So this, or a bead of sweat that drops down the end of your nose, is going to hang on the end of your nose. It's going to itch, you know? One of the things I was talking about was the spacesuit. And as people came back from various missions, they'd say, well, how is it? And you say, well, this joint's not so good. And this, bit by bit, they improved them. But the one thing everybody said was, if my nose itches, there's nothing I can do about it. And, you know, you can't scratch the outside. You can't scratch the outside of your helmet, but it's not going to do any good. You want to get your hand in there. Oh, that's lovely. You know, think about it. If you've got a tray of something, that's when your nose itches, isn't it? You can't get it. So people were saying, on Apollo 17, we had the solution. There was a little stalk that came out, and on it, there was some of that prickly Velcro. You know, you got Velcro on your shoes, maybe? And you could just scratch your nose. Perfect. Perfect.
Unfortunately, we have come to the end of our session. I was wondering if you had any sort of final comments or, pieces of advice or anything like that for our viewers today.
Well, look, I'm going to go back to my childhood. Some people say, you know, why did you become an astronaut? And I was a bit by chance, you know, my wife said, would you like to become an astronaut? I said, oh, yeah, you bet. I was flying in the Navy, and I had flown with the Navy to get onto aircraft carriers. So say to myself, I was a pretty good flyer. And I got a phone call out the blue. And sometimes, you know, people ring you up and you think, well, yeah, okay, I'll give it a go. But it was the big thing, you know, it was the big thing at the time. But the person who made me able to take that decision, to train as a pilot and therefore go the next step, was my father. Now, sometimes, you know, people say to you, you ain't done that properly. Your math homework, your geography report, or whatever it is. You ought to do that again, because you can do better than that. And that was my father. For example, we would do, I don't know, some carpentry or something like that. And you put this thing together and he'd say, it's not quite right. I'll tell you what we're going to do. We're going to go home, going to have something to eat, and then we're going to come back here. We're going to disassemble it. We're going to put it back together correctly until we get it right. And that was his attitude. You're never going to achieve anything in life just by turning up. You know, you got to work at it. You're going to learn the piano. You got to do the boring scales. You wanted to be, I don't know, an artist. You got to learn the colors. And if you're going to be an astronaut, you got to do the math, the training, and so on and so forth. And it seems a long slog. Now, whether you're going to be an astronaut, a pianist, an artist, a ballet dancer, whatever it may be, people may say to you, oh, forget it. You're never going to do that. Well, let me tell you this. Never do yourself down. You may not achieve it, but never, ever look at something and say, nah, I'm not going to bother with it. If you want to do it, look at the impossible. Work at it. And who knows, one day, the possible may just happen for you. And, you know, that's been my philosophy, and I pass it on to you. And as I say, just emphasize, now we've got a whole lot of people out there who are interested in space, not just half the population, but the entire population. Do it. Go for it. That's my philosophy. And I hope you've gained something from this, and you know, you'll want to look up some more information about not just Apollo, but space travel in general. Been really nice talking at you and seeing some of the faces over there. Really lovely.
Thank you so much, astronaut Gene Cernan. We've had an absolutely incredible journey to the moon and back. I'd like to say my heartfelt thank you from the Royal Astronomical Society. And to those of you that have participated and sent questions, thank you so much. We welcome any feedback, or if you want to get back in touch with us with further questions, please send them to my email address or via Eventbrite. Keep an eye on all the things that we've got going on during lockdown and onwards at our website, ras.ac.uk. And please do keep safe and well. Thank you very much. I can see some applauses and some thank yous from humans and dogs. So thank you again, Gene. Take care, and hopefully